Welcome back to Arxflix. Today, we're exploring a groundbreaking paper titled Can Kolmogorov, Arnold Networks. This research introduces a novel neural network architecture, KNs, as a potential replacement for the ubiquitous multilayer perceptrons, MLPs. This figure highlights the key difference between MLPs and KNs. While MLPs have fixed activation functions on nodes, KNs have learnable activation functions on edges, replacing linear weights with univariate functions parametrized as splines. Let's delve into the paper's key insights. MLPs, despite their widespread use, have limitations. They consume a significant portion of parameters in transformers, and their interpretability often requires post-analysis tools. KNs, inspired by the Kolmogorov-Arnold representation theorem, offer a compelling alternative. They leverage the theorem's ability to represent multivariate functions as compositions of univariate functions and addition. While the original theorem had limitations, this paper generalizes KNs to arbitrary widths and depths, making them more practical and powerful. This figure illustrates the key components of a KN. Each activation function is parametrized as a B-spline, allowing for flexible adjustments and switching between different resolutions. KNs are built as compositions of layers, where each layer is defined by a matrix of 1D functions. This allows for stacking multiple layers to create deeper networks. The paper presents a theorem demonstrating that KNs can approximate functions with a residue rate independent of the dimension, effectively beating the curse of dimensionality. This is achieved by using splines to approximate 1D functions, allowing for efficient learning of compositional structures. The paper also explores neural scaling laws, showing that KNs achieve a scaling exponent of 4, outperforming MLPs and other theoretical bounds. This figure showcases the effectiveness of grid extension in KNs. By fine-graining spline grids, KNs can achieve higher accuracy without retraining from scratch. The training dynamics exhibit staircase-like loss curves, indicating significant drops in loss after each grid extension. This approach allows for a more efficient exploration of the parameter space, compared to traditional scaling methods used for MLPs. The paper introduces techniques to simplify KNs and make them more interpretable. These include sparsification, visualization, pruning, and symbolization. Sparsification uses L1 and entropy regularization to favor sparse connections, while pruning removes unimportant neurons. Visualization techniques highlight important activation functions by adjusting their transparency based on their magnitude. Symbolization allows users to identify and fix activation functions as specific symbolic forms, further enhancing interpretability. This figure demonstrates the interpretability of KNs on various symbolic tasks. KNs can effectively reveal the compositional structures present in these formulas and learn the correct univariate functions. For example, KNs can learn the multiplication of two numbers by leveraging the identity 2xi, xy, 2, x2y2. This figure showcases the application of KNs to unsupervised learning. By introducing positive and negative samples, KNs can identify groups of dependent variables without requiring manual splitting of features. This approach offers a significant advantage over supervised learning, as it avoids the combinatorial explosion of possible feature splits. The paper demonstrates the potential of KNs in scientific discovery by applying them to knot theory and Anderson localization. In knot theory, KNs rediscover known relations between knot invariants, achieving higher accuracy and efficiency than previous methods. In Anderson localization, KNs help extract mobility edges from numerical data generated from quasi-Parikh tight binding models, demonstrating their ability to identify complex relationships. KNs offer a promising alternative to MLPs, showcasing superior accuracy, interpretability, and efficiency. Their ability to beat the curse of dimensionality and achieve fast neural scaling laws makes them a compelling choice for various tasks, particularly in scientific domains. While further research is needed to address limitations and explore new applications, KNs demonstrate the potential of AI-scientist collaboration in scientific discovery. Thanks for watching Arxflix. Don't forget to like, subscribe, and share this video with your fellow researchers. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.